occasionally sequences with factorials show up in calculus, and actually quite often series with factorials show up in calculus. So I think it's time to start practicing a little bit with how to manipulate factorials. This particular problem is just one of those clever proofs that you have to be exposed to start to understand the style of how you would approach a problem like this. So I wouldn't expect you to get this before seeing it done once. And the way I'm going to handle this is to start just writing out the first several terms of the sequence and see if I can detect a pattern and something useful that I can do to get a handle on this thing. So undoubtedly, the numerator and the denominator are both getting very large as n goes to infinity. Factorials and exponentials both grow incredibly fast. And in a sense, I'm just asking which one of them wins here. So let's look at a1, plug in n equals 1. And I get 2 over 1 factorial, which is 1. Now let's look at a2. In the numerator, I have 2 squared, which is 2 times 2. In the denominator, I have 2 factorial, which is 2 times 1. Let's look at a3. It's going to take a while to see what to do here. In the numerator, I have 2 times 2 times 2. And in the denominator, I have 3 times 2 times 1. a4. In the numerator, I have 2 times 2 times 2 times 2. And in the denominator, I've got 4 times 3 times 2 times 1. So you might be getting a sense at this point that the factorial is winning because it's tacking on a term that's bigger than the corresponding term tacked on in the numerator every single time. All right, and now it's time to sort of cleverly set up an inequality here. So what I notice in a2, so n is 2 here, I could say that a2 is equal to 4, because I have these 2 factors in the numerator, over n. Now it might seem a little curious that I would write it that way, but let's try to do something similar in the next example. So n is 3, and if I cancel one of these factors of 2, I end up with, again, 4 over n. So now let's look at a4, and I'm not going to have an equality anymore. I'm going to end up with an inequality. So I'm looking at sort of pairing up. I could cancel these 2's, but I can't cancel another 2. But I do see that I have a 2/3 that I could highlight. And so what I'm going to say is 2/3 is less than 1. And so this expression on the left is going to be less than, and I'll go ahead and throw in an or equal to cover those first 2 cases. And I have a 4 in the numerator, and then I have an n in the denominator. Let's continue this process to see if it remains true and if we can really convince ourselves of this inequality. I'm going to cancel those 2's, and then I'm going to say, well, 2/3 is less than 1, but 2/4 is less than 1. And so I end up with a5 being less than 4 over n. Again, let's do one more, and then it should really solidify the process. So I have 2 times 2 times 2 times 2 times 2 times 2. That's a lot of 2's. Over 6 times 5 times 4 times 3 times 2 times 1. And I can cancel these 2's. I can say 2/3 is less than 1. 2/4 is less than 1. 2/5 is less than 1. And I end up getting something that is certainly less than 4 over 6, or 4 over n. And this continues. So we can conclude from this that my ANs are always less than or equal to 4 over n. But I also know that my ANs are all positive. 0 is less than AN, or AN is bigger than 0. So what I'm doing here is setting up the squeeze theorem. And certainly the limit as n goes to infinity of 0 is 0. And the limit as n goes to infinity of 4 over n is 0. And by the squeeze theorem, this means the limit as n goes to infinity of an, or 2 to the n over n factorial, is equal to 0. So in the end, this sequence converges, and it converges to 0.